So earlier today, Jean Sebastian in one point he said that he uses the numerics purely for evaluation purposes. It sounded kind of like I'm sorry I use numerics. So just to be clear, I'm completely unapologetic about this. I'll talk about simulations, numerics, okay? Okay, so the spirit is still exactly the same as last time. So we want to learn about the physics by trying to simulate it. So as I mentioned yesterday, so we have this today, the second lecture is still kind of in this limit where we're gonna keep the state vector as an exact quantity. So I still only gonna talk about relatively small system simulations. And then I kind of want to lead to this, in the third lecture, to these large system cases. In particular, this morning you already heard about DMRG being a very useful tool. That's exactly what I want to talk about in the third lecture. I will talk about DMRG, but in kind of this modern language of matrix product states. But before that, I stay in the small system, so I want to keep it simple, just review a little bit of some spin model physics that I want to show as an example for the calculations today. And then the two important pieces of today are the so-called Krylov space methods, which I think are really a cool approach. They tell you something about really how dynamics works in a quantum system. And then in the second part, I will talk about some open system methods, so how we treat really open system dynamics. Good. So just as a reminder to connect to the last time. So last time we really just discussed fundamentals on how do you write down numbers in the computer memory and how do you write down state vectors and just the general linear algebra problem of having a Hamiltonian that you have to diagonalize. But then not all problems are of a linear nature, and in particular, if we start to want to treat large systems, we can make these mean field approximations. As example, I had introduced sort of the Gross-Petersky equation, which comes from the fact that we take a quantum field theory, we make it classical, which is equivalent of saying we have no entanglement between the particles of the different states. And by that, we can sort of treat much, much larger systems. But of course, we get this nonlinearity and we make a strong approximation. But still, these nonlinear problems we can also numerically integrate. I introduced this general Runge-Kutta type of methods. And then we looked at some type of fun with Gross-Petersky equations. In particular, I talked about this dynamical instability in 2D and 3D. Okay, but sort of today, three parts, as I said before. So the first is really just to introduce again a model of the day. And here I want to talk about long-range spin models. So really the type of spin models that we heard already earlier, but with long-range interactions. And then in the second part, I want to introduce this Krylov space method, how we simulate these models, and then go to the open system case. Good, so the type of dynamics that I want to look at here for an example is this type of either sort of this transverse easing model here or this long-range XY model. And this was something that was very fancy, like in the year 2014, when they had this kind of ion trap experiments, because the nice thing in these ion trap systems, what one does there, one can just trap the ions, and then one can couple the internal degrees of freedom of these ions to some motional states of the whole ion crystal. And thereby one can effectively realize these spin models. So one can effectively realize these easing couplings or this type of long-range XY couplings. And the nice thing is that one can tune this range of interactions. So the coupling strength here is not nearest neighbor, but it's really long range. And here it is the case as a power law with some exponent alpha. And in this type of setups, they could exactly analyze the difference between the physics when you change the alpha somewhere around the dimension of the system. So you can go from this sort of short-range physics when you take alpha equals 3, where the actions decay quickly. You can go to something like smaller than 1. Here an example calculation of 1.19. And then what experimentalists did in this, they did just fun stuff. For example, take an initial state where you flip one spin, and then you just see how this spin kind of propagates in your system. Or probably more excitingly, they can prepare this sort of very highly excited state for this type of model, and then you look at some spin-spin correlation. So this is really a two-body spin-spin correlation as a function of time, and one sees how these correlations are spreading out in the system. And that's just to motivate, that's the type of dynamics I want to simulate today. Okay, so just as a reminder again, so this is just what we did, it's a repeated slide from the first lecture. So quantum mechanics, we want to have our state vector description. So we have our d-dimensional Hilbert space, so we have these d elements in this vector, d complex numbers, and we have the Hamiltonian matrices, which are these d by d matrices. And again, I mentioned the state vector is not limited to really quantum state vectors. Also later we'll see how we have an open system, then we can also linearize like the density matrix in the system, or classical particles also can be written in this form. Okay. All right, so, but I have not told you sort of how to actually, in practice, to construct these Hamiltonians on a computer. So I want to start really slow, sort of a kind of like easy introduction of how one can actually get to this big Hamiltonian matrices, because these are going to be big matrices that grow exponentially with the system size. So how are we actually building them? Good, so, and I will stick for now to this transverse type Ising model. So of course, the important thing to realize if you write something down like this transverse Ising model, you write something down carelessly like sigma I of x, meaning you have a Pauli operator acting on the spin number I. But of course, what you actually mean by this is that you just act only on the spin I, but you apply an identity on all the other spins. Right? So if I write this really as 2 by 2 matrices, I use this tensor product, or also called the Kronecker product, between the identity matrix for all the other spins except for the spin I, where I have a tensor product with the sigma x matrix. The same is true for these two-body terms. Right? What we mean by these two-body terms is technically one should write something like this, sort of tensor product identity on the first spins up to the first spins I, then I put a sigma C matrix there, and then identities, then another sigma C matrix, and then identity matrices. So here I use just a convention where my spin down is, for example, state 1, 0, and the spin up is the state 0, 1, and that's why the -1 in the sigma set is up here. Okay, so fundamentally, what I want to convince you is sort of a very elegant way of just constructing any type of Hamiltonian on your computer memory is by just first constructing like the spin lowering operator, sigma minus. Right, so this is the simple operator here. So you see if you act with this on the spin up, it takes you to the spin down. So the way that this operator looks really on the big Hilbert space, on the 2 to the n times 2 to the n Hilbert space, it looks something like you have an identity matrix, which is 2 to the I minus 1 dimensional on the left side. Then you do a Kronecker product with this lowering operator here, and then a 2 to the n minus I identity operator on the other side. Right? And this is going to give you the 2 times n to 2 times n matrix of this operator. Okay, and that's what I want to convince you. That's what I want to do. So these operators, they are really easy to construct. Like here again in my Julia language programming example, you can really just do something trivially like this. You say, okay, this is your sigma minus operator, just defined for a single spin. And then what I do here, I just define like a vector of the operators. So for each spin, I want to have my sigma minus operator. And then I just always loop here through all the spins. And then on the left side, I create an identity matrix of this exponential left side dimension. On the right side, this right side dimension. And in the middle, I just squeeze in this sigma m. So this is really just this Kronecker function, which gives you this tensor product between these three matrices. Okay, and with this, then you're actually done technically, because from this, you can construct really everything, just using this operator. Why? Because, I mean, we know, for example, if you have a Pauli X operator, which is for the transverse field here, we know the Pauli X is just sigma minus plus sigma plus. So I can really just write this now with this sigma minus operator for spin I plus the dagger of this, because the dagger of sigma minus is going to be sigma plus. And this is going to give me, if I sum over all the spins, it's just going to give me this transverse field part for all of the spins in the system. Same with the sigma C operator. Sigma C is just sigma plus, sigma minus, minus, sigma plus. So I can just really construct it like this in there, right? So all of these products here, they are just matrix products, and all of these little dashes here are just really Hermitian conjugate operations. And that's it. And with that, you have the Hamiltonian, and then you can do stuff with it. Now, one important concept that I want to get across is, of course, if you do it like this, it's going to be extremely inefficient. Why? Because let's have a look at this Hamiltonian matrix here that comes out. So I take here the matrix, how it's going to look like for a system of 10 spins. So 10 spins mean you have a Hilbert space dimension of 2 to the 10, 1024. And if you look at this matrix, of course, it's going to be 0, 0, 0, almost everywhere, right? Because this is a situation where I have long-range couplings. So my Ji is an n by n matrix, which is full, right? So all the spins, all the two-body terms exist in the system. But still, of course, my matrix is a 2 to the n times 2 to the n matrix. And of course, most of these elements here are still going to be 0. Right? To be more precise, and it's something I one can check actually numerically very nicely, because actually the number of elements in my matrix, so my matrix has 2 to the 2n elements, but the number of non-zero elements is only something of order 2 to the n, right? So, and whenever you have a situation like this, where you have sort of not all the quadratic amount of elements occupied in your matrix, but just a linear amount, then it pays off to use something that's called a sparse matrix. Right, so here I take this matrix, this is a simple command to check, for example, how many values in this matrix are larger than 0. 0 I define again by my numerical threshold. That comes from our precision that I introduced in the first lecture. And I see I get this small number, I divide it by 2 to the 20, which is 2 to the 2n, and I see that only 1% of the numbers are actually non-zero. So in a sparse matrix, right, you can think about how you write down this matrix. So here, if I do it like this, I write every element in the memory, even all the zeros. On the other hand, if I have a sparse matrix, I just make like a table where I say, okay, element 1, 2 is this number, element 2, 3 is this number. And I only keep the elements which are larger than 0. And then this is much more memory efficient. The good news is this is something which is extremely easy to do. This is exactly the same type of thing I showed you before. All I have to do is, instead of when I start with my sigma minus operator, I just make it a sparse operator right from the beginning. Right? And then if I do all my Kronecker operations, they will always remain sparse. So the only changes are highlighted here in this little blue background. Is I make this first matrix sparse, and then I add like sparse identities in my Kronecker, and my Hamiltonian starts to be of a sparse matrix. And then if you just print the output of this, you're going to get some graphical depiction of this. So this is sort of this whole matrix, and the non-zero elements are these little dots here somewhere. So you see how this matrix looks like. You see it's 0 almost everywhere. And this really pays off. If you do this with like a full matrix, as I showed in the first example, it's going to take a minute. And here it's something like 10 to the minus 3, so milliseconds. So like 5 orders of magnitude speed up is something that you'd want to look for. Okay, so this is just a practical example. So now what do you want to do if you simulate something with this Hamiltonian? You have now the Hamiltonian. You can just use it to do your algorithms. I will show you then in a minute what's a very good algorithm to use. But then, of course, you also want to define some initial state. Also initial state, same thing. You can use this Kronecker type product. So you have a spin down and a spin up vector, and you just do a tensor product between them. It's going to give you your initial state. Or you're even more simply, you know that the all state with all are downs is the state where like all of the states are 0. So this is just really a vector with 2 to the n elements, and only one element, the initial one, is 1. Same is true if you want to, of course, compute some dynamics. I want to have some expectation value. I can define my sigma z operator for my spin j, again, just from these lowering operators, and then just compute expectation values with simple matrix products. Okay, and that's a very, just give you kind of engineering type introduction to how to construct this type of matrices. The same you can also apply if you're interested in Bose-Hubbard models, for example. In Bose-Hubbard models, of course, you don't have the spin lowering operator, but you have the local boson annihilation operator. So you have to define this as a sparse matrix, and then you have to define things in such a way that, for example, your n equals 0 state is the vector where only the first element is 1 and the other ones are 0. The state 2 is where this one is 1. And then if you destroy a boson on this side, you go from this one with this with a square root of n outside. So one has to construct this as a sparse matrix, which only has the upper diagonal filled with a vector that's goes like 1 over the square root of number of particles. So you can just check that this works. But of course, a word of caution here. If I do it like this, I have to introduce some type of maximum number of bosons sitting on a particular site. And then, of course, it means that I have a grand canonical system. Right? This means I have all of the states with different particle numbers in the system. Right? I showed you in the last lecture, if you take the Bose-Hubbard model, you look at the Hilbert space dimension. It was this combinatorical formula. If you do it like this, it's just going to grow exponentially with the number of sites. So if you want to treat 100 sites with 5 particles, which you can totally do with exact diagonalization, you cannot do it if you do it that way, because here you keep all the blocks of different particle numbers. So if one wants to conserve the particle number, one has to be a bit smarter. Okay, but enough of this. This was just a mild introduction for showing you how simple it can be to actually construct your matrices, just standard linear algebra. Okay, But now the question is, we have now something like this Hamiltonian, and we want to simulate some dynamics, and we know these Hamiltonians are very sparse matrices, and we want to kind of use the fact that those are sparse matrices. And there, the methods I introduced are the so-called Krylov space approaches, and I want to give you a general overview. This is a whole field of different type of algorithms, and I just want to give you the main idea of this Krylov space. Okay, so again, let's just redefine our goal. Our goal, and I want to look at the time evolution. I take some initial state, think about my long-range spin models. I take my initially flipped spin state, and then I want to know how this evolves as a function of time. And already last time I showed you we can use this Runge-Kutta method. Totally doable, you can just do it, but it's a bit overkill. It's overkill in the way because the problem is actually here we have a Hamiltonian, so this is really a linear problem, and also the Hamiltonian is time independent. So, and this Runge-Kutta is actually not necessary, and there can be easier, better ways. So a more better way would be just to try to sort of do some matrix exponential. Unfortunately, what I introduced as exact diagonalization in the first lecture would be sort of you compute all of the eigenstates and eigenvalues of the system, and then you evolve, you create this matrix, which is the time evolution operator, and you apply it to a state. The problem with this is that if you have a sparse Hamiltonian, if you compute the n eigenstates, in general, all the eigenstates are going to be filled. Right? So if you now, if you really now do the spectral decomposition of your Hamiltonian, so you get in generally this matrix where you project on the eigenstates, and all of the eigenstates are all full vectors. So in general, you will get your matrix exponential is going to be a full d times d matrix. Right? So then all the advantage that we lost, that we gained before, that we needed only sort of d elements in our Hamiltonian instead of d squared, would be now gone if we do that. So we have to do something better. So the intuition behind this, what I'm going to talk about, is just if I look at this matrix exponential, so the time evolution operator, if I expand it just in this Taylor series, I can define this matrix, let's call it, I do this complex number minus it, I multiply to the Hamiltonian, and then I just write it as this matrix A to the power of k applied to some initial state that I have. So if I look at this, then of course the intuition is I mean, here I sum over all of the eigenstates, but in practice, why would I sum over all of the eigenstates? Probably only a few of them are actually important for understanding the dynamics of my system. And that's fundamentally the idea of this Krylov space method. So the general idea is if I look at this term here, I have all of this sum with a to some powers k. And sort of the Krylov space is kind of a space that I introduced that should be kind of optimal to, to solve this thing. So you see kind of the states that would be a good idea to use would be what's called the Krylov space. Is I take this matrix A, I apply it like not at all to my initial state, and that's my first eigenstate in the system, my first state in the system. And then I apply this matrix 1 time, I apply it 2 times, I apply it 3 times, and so on. And it somehow seems like a good idea to actually use this basis for doing this matrix exponentiation. So this is called the Krylov space. It's named after this guy here, and before I just looked again on Wikipedia some numbers up, because nowadays we tend to complain about how much we have to publish. But then this guy published about 300 papers and books in fields like shipbuilding, magnetism, artillery, mathematics, astronomy, and geodesy. So it should be.
But did he have to work for a living?
No, he came from a very noble family. So also that was already in the system. So yeah, our problems nowadays are not so new. Okay, and the idea is if we want to build this matrix exponential, let's do it on this basis, because that seems to be a good basis to use. Now, the fundamental problem of this is that these states that I define here by just blindly applying my matrix to the state, they are not going to be orthogonal. Right? And one simple way to see this, and I just do this by, on the side, introducing a funny method. Let's for a second say that A is really the Hamiltonian. Here it's actually imaginary unit multiplied with the Hamiltonian, but let's say it's the Hamiltonian for a while. And then let's say you apply now this Hamiltonian to states. Then of course what I can do is my initial state that I have and that I use to define my basis. I can of course expand the states in the eigenstate of the Hamiltonian. So let's say I have some eigenstates, so with eigenvalue En, and the eigenstate is also called En, and I just order the energy of these eigenstates from the largest to smaller ones. And then just consider what happens if you apply this Hamiltonian k times to this state. Well, of course, these are eigenstates. We're going to get this sum here, so Cn, whatever the initial state is. And then you see it because if you apply e to the power of k, then of course the by far largest term in this sum is going to be corresponding to the eigenvalue which is largest. So what happens if I take this state and if I of course, I mess up the norm, but if I renormalize the state, then this is going to be approximately the highest energy state in the system. And that's like the most ridiculous way to compute sort of the highest energy state in the system. You apply the matrix, you renormalize, you apply again, you renormalize. And it's called the power method, and it's fascinating, it works. So that's a simple way of computing a ground state. Of course, ground state, you have to just flip the sign, and then it's going to work. Okay, of course, your initial state has to have some overlap with this state. That's a condition. Okay, but you see already the problem. So these states, when I apply multiple times, in this example, my state just rotates closer and closer to the highest energy state in the system, which means that these states for higher k, they get more and more actually aligned with each other. Right? So, but I want to have orthogonal states to define my problem very well. So the work that we have to do is we have to take these states and we have to construct an orthogonal basis for them. So in other words, I'm sure many people are familiar about this. We have to do a Gram-Schmidt type procedure of this type of basis states. Yeah, by the way, so I formulate here in this bracket notation with heads as operators. Of course, this is a very general scheme. Was originally invented for some ship engineering or something. So it has, you don't need to use bracket notation, but it's just, we are so used to it, so let's use it. Okay, so here's how it essentially goes. It's really very simple. I think you probably heard of Gram-Schmidt before. So again, we take our initial state. We can just normalize it just in case, but let's say it's a good quantum state. And of course, this is a basis I define based on the state that I already have. So I take this state, then I apply I take this first new state here, this A1, I apply A to this initial state. And then, of course, I have to make this state orthogonal with the previous state. So what I have to do is I have to compute the overlap between the initial state and this new state, psi1. Let's call this number H11. And then I say my new state, psi1, is the old state minus this overlap. So to make sure that this state is orthogonal. But then, of course, my state psi1 is not necessarily yet normalized. So the next step, I compute the norm of this state. Let's call this number H21. And then just divide by this. And that gives me the vector psi1, which is normalized. And that's just already the whole trick. What I then just do, I do this whole thing many, many times. So then I take my state 1 that I got out here, and I compute my state 2. Right? And now what I have to do is I have to subtract 2 previous states. So I do the same thing. I just compute overlap with the state psi0. I call this number H1i. And then I take my state and I subtract this number. And now one important little detail, which is a little bit hidden here. So here now I compute the overlap again with the first state. But now I take already the new state I get out from here. Right? That's, by the way, that's known as improved Gram-Schmidt, because Gram-Schmidt tells you just take a state, you subtract all of the overlaps of that state with the initial state. But here I do an iterative way of just getting in this inner loop the new state already from the one that I update in the previous one. Okay, and if I do this, in the end, I renormalize again. I'm going to get, in the second iteration, I'm going to get a second state, which is now orthogonal to the previous two ones, and so on and so forth. So this scheme is called the Arnoldi iteration. It's from a guy where, strangely, you really find no picture on the whole internet. So it still exists. Okay, good. So let's think a little bit about what we are actually doing if we apply this scheme. So here's just exactly the thing from the previous slide. So on the one hand, we get all of these states here. So here I call them state psi I. These are now my new states. So the first state is, of course, the original state. It doesn't change. Then the psi 1 is one, which is orthogonal to this one, and so on. And I get, if I do sort of I plus 1, so if I do this iteration I times, I get I plus 1 orthogonal vectors. Right? So I can think about now this matrix of these new vectors that I get. Let's call it Q. And what this matrix really does, it's a matrix that can project you from your Hilbert space to this Krylov space. Right? So this is a so-called semi-unitary matrix. It's a unitary in the sense that if I take qi dagger, it's going to be an identity, because of course all of these columns are orthogonal, but it's not a square matrix. That's what you call semi-unitary. Anyway, it doesn't really matter. So this is really, if you think about this, it's really, so this is, the Q is the one that takes you from Krylov space to the Hilbert space, and the Q dagger takes you the other way. So if I have this Krylov vectors here, this Qi is really a projection matrix to these Krylov bases. Now, the question is, why did I name these numbers that I got out of the iteration and that I stored in a matrix? So what do they actually mean? So I called these elements here 1i. So if I write them really as a matrix here, I really get this I plus 1 times I matrix. And this matrix is in the so-called upper Hessenberg form, which means that it has everything above the diagonal, and the diagonal is larger than 0, and one subdiagonal is also larger than 0, and all the other elements are 0. I get this simply because in the first iteration I get two numbers. The one is the overlap with the first state, and the second one is the norm. And then in the next one I get three numbers, and so on. I just fill up this matrix. Okay, so what is this matrix, and why do I actually call it H? Again. So I think the best way to understand this is to realize that if I look at this iteration, I can write it in this particular matrix form here. To prove this fully exactly, I leave it as an exercise, but you can easily see it, for example, from the first iteration. Let's say I take my state psi1 that I got from this iteration. The way that I got this is I applied A to psi0, the initial state, then I subtracted here this overlap of the initial state, and then I divide it by the norm. Right? So if I just massage this equation a bit, I can write this as A psi0 is h11 psi0 plus h21 psi1. Now I can think about this thing on the left side here as a 1-by-1 matrix. And here I think that I have this vector here multiplied to this first column of this matrix. Right? So this whole iteration procedure here, I can just write it for the step number I can write it in this type of matrix form. And then, of course, one uses induction to prove this for all the higher i's. Okay, so what is this matrix that we are filling here? Of course, I want to stop at one point. I don't, the intuition is, we need a certain amount of these Krylov vectors to do our matrix exponential. But of course, we don't want to go to the full Hilbert space size. So at one point, we're just going to stop this iteration. So what does this mean if we stop? So at one point here, I have this matrix Q that I start building, and I say I have my vector I. And then there's this new Krylov vector at I plus 1 that I could still build, but let's just say we throw this vector out, and for some reason, it's not important. Well, equivalent thing to do is I can say, okay, let's forget about this, but I can also take my matrix Hi, which is this, I did earlier, this is this I plus 1 times I matrix. And now I just erase this last row here, because this is the one that would multiply with this term. So I erase this, and I call this H tilde, and this is the matrix that I get in my last iteration. Right, which means that in the last step, my Qi plus 1, which would be the one for the next iteration, applied to H, I approximate it by this Qi times this H tilde matrix. Now, if you take this equation, you plug it in here, you see that this is equivalent of saying that HQi is approximately QiH, and this Qi is this kind of semi-unitary matrix, so I can write it also again in this form or in this form. So you see exactly this Hi tilde that I produce with the iteration. It's actually the form of the matrix A itself in this Krylov space. Right, I call it here H because you can do it for Hamiltonian, and then that is actually the Hamiltonian representation in this new space that we constructed. So we don't have to transform the Hamiltonian, but we get it automatically out from this type of iteration. Okay, so the whole idea of this is now these Krylov space methods is that one does some type of iteration. Of course, one has to do this in every time step. I construct a new basis at every point in time because it's only defined for a particular state. But then I just construct this space, it should be small enough, and I get sort of my matrix that I have, and then I do everything with the matrix I want to do. For example, find the values eigenvectors, or do, in our case, the matrix exponential. Okay. Ooh. Something's happening. All right, so good, so that's what I just said. So this matrix that we get is an approximation of the matrix A. Of course, I have not really proven that it is. As I said, I will skip this type of proofs. At one point, we have to check when to stop this iteration. I will just show you with numerics how it actually really is going to work. So now we do exact diagonalization of this small matrix. So just a little comment here is I showed it for general matrix A because in our time evolution we have imaginary unit multiplied into this matrix, so it's not a Hermitian matrix anymore. But if your A is a Hermitian matrix, like a Hamiltonian, then actually one can make this iteration even more efficient. And instead of this upper Hessenberg form matrix, one can also find a representation which has a tri-diagonal form that uses a slightly different iteration. It's called the Lanczos iteration. And this is very useful for finding eigenstates of the system, a few eigenstates. But I want to talk about time evolution, so I stay with this general Arnoldi method. Good, so this is how you would do it. Again, really only just a few lines. So what this whole function is doing here, this is really this blue box here, is this iteration. I just marked it blue over here. And that's exactly what you need to do. So this is this function. You have this matrix A, you have your initial state. And what this function does, it just creates this type of representation of this matrix A in this Krylov space, then does a matrix exponential of it, and then it just gives back the result of the matrix exponential applied to some initial state. So this is just preliminary stuff. Yeah, I actually said that I would distribute the slides. We have to discuss how to organize this. I can send it to you maybe, and you send it to everyone. So I don't want to spend too much time on details, but I encourage you to go through that. So really everything is here. This is this Krylov state iteration. So I just create m of these Krylov state vectors in this loop. Again, this is really just iteration. The first step here, I apply the matrix to the previous one. So my matrix Q, I start building. This is a matrix which is D times M. So D is my Hilbert space dimension. M is my Krylov space dimension. So this is the matrix that takes me from one space to the other one. And I just apply this to the state, the first column in the previous iteration. And then I do all this magic. I compute my matrix elements. And I get the new iteration, which I put then in the next Krylov vector over there. Also here constructing this lower element. And then I do the matrix exponential. All of the hard part is actually hidden here in this tiny thing. This is a full matrix exponential, but now for very small matrix, because this Krylov vectors, I choose something like on the order of 10, so a matrix exponential is essentially free. And then technically what I do is I do something like I wrote in the equation here. So I have then my initial state. I project it to the Krylov space with this QM dagger matrix. I do the matrix exponential, and then I project it back into Hilbert space. And that's an approximation of my state e to the a psi 0. But because actually my psi 0 is already in this matrix here, it's actually the first row in this matrix QM dagger, right, just by construction. That's why I actually can return just from the matrix exponential the first column, and that's going to be it, multiplied with this Q matrix. Okay, so again, this needs a few comments. So first of all, let me show you how this works in a very stupid example. This is really running just this function here. I just take, so let's say I have a Hilbert space of a dimension 1000. I use 20 of these Krylov vectors. So let's just create some random Hamiltonian. Just last time, this is really a completely random Hermitian matrix. I multiply some imaginary unit and some time unit. I'll come to this in a second. And I take some random initial state, which I normalize. And then I compare if I do the full matrix exponential, right? This would be just, I get exact diagonalization state from the full matrix exponential applied to my initial state, or I apply this function, which should do the same thing. And then in the end, I just check the overlap squared of these two terms. And here is what you get. You get really perfect overlap, right? So with these 20 Krylov vectors, it's really a perfect approximation to the state up to machine precision. But I'm something like 2 orders of magnitude faster, which is really nice. And this is for like a random full matrix. So if you have a sparse matrix, actually the advantage is going to be even more. Yes. So question is, how many of these Krylov vectors are we going to need? And there's kind of like, I show you here just the numerical result. So this is really running this thing with this approximate version. And what I plot here, I can take again my Hilbert space size of like 1000. I plot here 1 minus the fidelity. So this is really telling you so how well the overlap of your ideal state is with the state that you get from the Krylov approximation. I think I have a typo here. I think this should be T. Sorry. But then you see I take this random Hermitian matrix and I just simulate a situation with some type of time step, and I make the time step larger. So I take it 0.1, 0.2, 0.3. And here's the number of Krylov vectors that you use, and this is the error that you essentially get. And then, of course, you see that really this effective Krylov space that you use for doing your actual time steps calculation, it actually depends on like the time step size. So if I make a larger time step, I'm going to use more Krylov vectors, which is very intuitive, because if I want to evolve my system over a very large step, I need to involve many eigenstates in the system, many powers of this matrix applied to my initial state. But technically, I mean, this is ridiculous. This is like something on the order of 20 is really essentially free. So it's, and 0.1 is always a good time step to use. So this is really a very nice method to use. Okay, so just a quick comment. Of course, this is really the easiest way of doing. Of course, what I didn't discuss here now at all is any type of stopping criteria, because in practice, of course, you want to go in your Krylov space and you want to check for convergence. You want to check how good your approximation is, and then you want to stop at one point. I didn't discuss this at all, and just mentioned there are many toolkits out there. So for Julia, for example, this Krylov kit or this Expo kit, who does exactly the thing I did here. Only advantage, they have also very good error estimates and error stopping criteria. So this is something now that one understands how it works, one can happily use. All right, so how does it work? So again, this is just kind of like doing a summary of like all of the code that I discussed and how it works. So the goal was just going back to the physics motivation. We have these transverse easing models, which have these long-range terms and this transverse field. So here I have a little example, just creating this kind of coupling matrix, this Jij. Here was just this little loop of how I create the Hamiltonian using these sparse sigma minus operators. And then I have an initially highly excited state. So for example, what I look here is initially I start from a Néel state. So I say I have initially a state where I flip all of the spin on the odd sides, I flip it up. Sorry, on the, yeah, this is the other way around. So here I have the little loop. I start from my state where all the spins are down, and I just apply the creation operator on all of the odd sides of your system. So this is up, down, up, down, up, down, up, down. And then I just run a time loop with this Krylov iteration that I just mentioned. All of it maybe something like 50 lines of code. So there's really not more to actually do. Good, so let's just discuss a little bit of the physics. You already heard a little bit about this before. So here I show some example of like 22 spins. This is something you can easily do still on your laptop. And this is the typical evolution you get if you look at the short range case, right? So alpha 3, this is what we heard in the first lecture today as an example of being essentially really nearest neighbor physics. Alpha 3 in 1D means that this coupling matrix decays in a like dipolar form. And here you see the time evolution, so time is going up. And here on the x-axis, I just label the different spins. So you see initially the Néel state, I start with spin up, spin down, spin up, spin down, and so on. And then what happens is actually incredibly boring. You see you have some type of oscillation, and then everything goes white, which means all of the spins go to zero. Right? So in the end, why does this happen? Well, it's pretty boring in a way, because you can think about like take one spin in the middle, and then kind of like all the other spins act like a bath for my spin, right? So my spin is going to thermalize in general. So what I expect is that if I just wait long enough time, my spin is going to go to this maximum entropy state here, which means that the sigma c is going to be 0. On the other hand, if I now go to this very long range case here, so this is alpha 1, there you see that you sort of clearly start to sorry, the contrast is a bit low on this projector, but there you clearly start to see these oscillations that are collectively starting to happen in the system. Right, this makes perfect sense, because this long-range physics one can very nicely understand just by rationalizing this infinite range limit. Right, if you go to alpha 0, what happens then? And then all of the couplings between all the spins are the same, And then I can just really pull out this coupling strengths outside of this sum. And then I see I get collective dynamics. I can write this in terms of collective spin operators. And then like all of the spins are doing all the same thing all the time. And that's happening over there. Sort of more interesting is maybe looking now at this correlation function in the system. Again, this is for this short-range Kant physics now. Both the left and the right are both for this short-range like case. And here what you see is going to happen. So this is really a connected correlation, right? So I'm kind of like subtracting the trivial classical correlation I have in my nil state in the beginning. So I'm really interested in how much quantum correlations am I building up here in the evolution. And I see that here I first sort of like this is as a function of the distance. So the distance between the spin I and j, and this is time again. And I see first like the first spin is going to spread some correlation to the next spin and then going to the next neighbor and so on. And this is going through the system. Overall, it's also going to very small numbers. Again, because if I pick 2 spins out of this spin chain, if I have nearest neighbor physics, my system is going to thermalize and effectively this is going to go to 0. So I see, however, more interesting physics if I plot this whole thing on a log scale. This is exactly the same plot. The same plot, I just use it on the log scale. And here you see clearly, for example, this kind of light cone-like physics, how correlations are spreading out. And that's one thing. But on the other hand, one also sees some interesting long-range physics here. These are very small numbers. I mean, this is 10 to the minus 8. But in some way, sort of the first spin is immediately start talking to the end spin a little bit. And this is really coming from this long-range tail of these interactions. So you may wonder, this plot looks kind of noisy and ugly, and one could be very suspicious that there's some numerical noise, but this is actually really true and fully converged. The reason why this looks ugly is because, of course, if you have sort of parts of these long-range interactions, they're going to immediately lead to some finite size effects on a relatively short time scale, which gives rise to this noisy type behavior. But that's an important, interesting aspect here, this interplay between this light cone spreading and this long-range correlation buildup. On the other hand, again, if I go to the long-range case, I see that, again, I see already immediately much longer range correlations building up immediately, so this kind of light cone behavior goes away. I still have a little bit of this stuff there, but then most of the dynamics is really sort of all of the spins get correlated and then they get here to 0, get recorrelated, and I see this collective oscillation. So there's really this interplay between these 2 things happening, and this has been like a while ago really in many papers discussed as an interesting type of physics object. But I just want to show you here an example as to really see that this is really something that one can do with minimal resources, just with a few lines of code numerically on your laptop. Good. So let me stop by a very unscientific comparison. So these are calculations done while traveling with a MacBook that even has some sand inside of it, and on like not even using power adapter on battery. I think it's maybe the more relevant comparison because that's what a PhD student usually does. And I just compare like the different runtimes here what I had. So the type of 3 methods that we kind of compared now was, on the one hand, what I could do is I can do this exact diagonalization step. This is, I just compute all the eigenstates in my system. And then I don't need to introduce any type of time step. I have the full matrix evolution operator. I can go from any time to any time I want. So here I go to a time tj up to 5. This is also for the long-range case. This is for alpha 1. And then I see sort of this is how much time it takes. I cut it off at 100 seconds because I'm not a very patient person. And you see this is going up here, and of course it's increasing exponentially. On the other hand, for comparison, I show now this simulation with the Runge-Kutta method here. And what you may wonder here is, I use a very small kind of time step here. And the reason for that is because, of course, I show an example where Runge-Kutta does not work. The reason is because here I have really these long-range couplings, right? So if I go to the alpha 0 limit, like all of these coupling constants in the Hamiltonian are kind of large. So the relevant time scale that I actually have that gives me the dynamics, it's not going to be given by this J, not by this spin interaction strength, but it gets collectively enhanced. It gets like a square root of n of J. Right? So if I have a large system, I have a very large quick oscillation, and I have to pick my time step small enough compared to this oscillation. So for Runge-Kutta here, I have to, for example, take this time step 0.005. Now, because I have long-range interactions, if I make my system larger, I have to make this time step even smaller. And with this, I get sort of a finite fidelity at the final time, which is still only 10 to the minus 5. But of course, if I use it, I can see compared to this straightforward exact diagonalization, it's still, it goes, you can do twice as much in the same time. It, of course, still grows exponentially. I come to that in the next lecture when I talk about larger systems. So here, everything I talk about is still exponentially hard when I make my system larger. But it's, it's a factor of twice better than this. So with exact diagonalization, you can do something like 10, 11. With this, you can easily go to like 22. But of course, by far the best is really this Krylov space method that I introduced, because there I can make the time step really large. I can get almost like machine precision fidelity, and it's even faster than Runge-Kutta. So this is really the way to go if you have Hamiltonian dynamics for exact state vectors. That's really, to my knowledge, the best method to use for this type of simulation. Okay, good. That brings me to the second part of the lecture. If you have any type of question, please feel free to stop me anytime. So in the second part today, so in the last part, so the first part we discussed sort of just how to create these Hamiltonians. Then I had this Krylov space, and now I want to spend some time talk about open system dynamics. So now we have to make the step of going from the state vector to a general density matrix in the system, and what's a good way of doing that? Of course, this is going to be a review, sort of many of you know, I've seen it on many posters. The type of dynamics I want to look at is master equation dynamics, and in particular, this Lindblad form of the master equation dynamics. So many approximations go into that to derive that. But fundamentally, you can think about, for example, you have some atomic system, for example, a two-level system. Let's say you drive the system with some coherent light. But then your system also couples to some environment. So your excited state can also decay. And then making a bunch of approximation, of course, dipole approximation, rotating wave approximation, most importantly, Markov approximation, you end up with this Lindblad master equation term that looks like this, which for this problem just becomes the optical Bloch equations. So, but in general, this works for any type of, or for many types of dissipation channels, sorry. So in general, I look at the evolution of my system density matrix. It's given by this super operator. So the super operator takes my density matrix. It represents the right-hand side of this master equation, and it has these two terms. The first term is just the von Neumann equation that gives you the coherent Hamiltonian evolution part. And then the second term has this Lindblad decay channel form. Has this form here. I have these two terms. I will discuss more in the next slide. And as I said just before, if you define these operators with some decay rate sigma minus, it's going to give you optical Bloch equations, which are written down over here. For many of you, this may look very familiar. Okay, and that's the type of equation I want to simulate. All right, so just to introduce several different ways of writing this, I've seen, I think, all of them on the posters today. So this is the one form. Of course, a very popular alternative form is that I say I can define an effective non-Hermitian Hamiltonian. So I define this thing here where I have the system Hamiltonian, which is my Hermitian matrix. But then from this, I just subtract minus I times this term of this Lindblad jump operators L dagger L. Right, and if I do that, you can see that I have these two terms that are over here. I can kind of absorb them in an effective Hamiltonian. I can write my first part of the evolution as this almost von Neumann equation. So here I had like really the commutator with the density matrix of the Hamiltonian. But here I have to be careful because my Hamiltonian is now non-Hermitian, so I have to write it like H effective minus rho H effective dagger. And then, of course, because this part gives rise to the coherent evolution, but it's a non-Hermitian Hamiltonian, so the norm of my state is going to decay. So I have to fix this somehow, and this is done with this second last term here that I keep out, which is for the reason, because it fixes the norm, it's also called the recycling term. In fact, just thinking about this in a very simple way, this type of Lindblad master equation form is really like the lowest or the easiest way to really write the proper evolution, because for a proper evolution you have to have, of course, the condition that the trace of a matrix is not changing. The trace is conserved. It should be 1. And you can see from the form of these Limplot terms here, in case you never remember the ordering of these terms, they are ordered really in such a way that here, if I build the trace of this second part, so the trace of the right-hand side of these Limplot terms, I have this term here. Okay, let's start from this term here. So what I can use, I can always use the cyclic invariance of the trace. So I can take, for example, this L dagger from this one, and I can put it on the other side. Here in this term, I can take this L from the right side, and I put it on the other side of the L. And in both times, I get this recycling term. So in total, that's why this factor of 2 is here. In total, then the trace of this thing is going to cancel. It's going to give 0. Right? So that's the only logical form to actually write evolution in terms of this type of jump operators that preserves the norm in your system. All right. Okay. So how do we simulate this? So I want to introduce several schemes to that. And sort of the first one is just, as I mentioned now many times, let's just think about our density matrix as a normal state vector. And then we can apply all of these methods that we already talked about earlier. So thinking about the density matrix as a state vector, of course, the density matrix is now a D times D matrix. But I can still think about, okay, I just order it in such a way that I write all the elements in one line. And then if I look at my master equation, I have some form of the super operator. It maps to some type of function of my state vector. And of course, I could just use this function. I could just write a function that encodes the whole right side of this equation. And I could use this as a function for my, say, Runge-Kutta method, for example. But that's not a very good idea to do because, of course, you may not see it from this Lindblad equation form. But actually, also this Lindblad master equation is just a linear equation. Right? So I can just, in the way, if I write this in the state vector form, and if I look at the time derivative of the state vector, then this function here, I can also just find a matrix A that multiplies to my state vector at times t. It's a linear equation. Which means, just like for the Hamiltonian evolution, the way that I can evolve this is just, again, building this matrix exponential of this matrix here. So we can use, again, our Krylov space stuff. Maybe you're not convinced that this is linear, but I think the best way to show is how to explicitly construct it. Okay, so there are several ways of doing this. I want to discuss this a little bit later. So what I want to do is I want to just take here, best introduce it with a simple example. Let's say I have a 3 by 3 matrix, so I have a 3-dimensional Hilbert space, and I have all my my elements of the matrix, and I have to order them in some way. So the way that I prefer to order them is just that I start with row 1, 1, row 2, 1, row 3, 1, and then I go to row 1, 2, row 2, 2, and so on. So I go column-wise. The reason why I do this is because in any reasonable programming language, the matrix is anyway stored in the memory in this way. Right? So your computer doesn't have a matrix built in. It just has a vector built in. And some programming languages store it in the row form, some do it in the column form. So, okay, so this really needs no work to transfer your density matrix to this state vector. Right, of course, I now have this linearized density matrix, so I have all these 9 elements here. And of course, I can map from my index in this vector here, I can get this index from the index j and the index I, of course, just using some very simple conversion. But I don't even need to do this because in the memory, it is already written like this. Okay, now one very elegant way to construct this super operator. It's sort of luckily this morning in the second lecture, you already had a little bit of a discussion of what this tensor product actually is. It's really like putting one matrix into the other matrix. So here, if I write just, let's consider just thinking I have 2 matrices, A tensor B, then I can write it in this form. I take just all the elements of A, and I just, on each element, I add the matrix B to the system. That's the definition of the Kronecker product in this form. Okay, so what I want to do is I want to now convince you that if you take this state vector in this form, so this is now really this 9-element vector. So what our Liouville matrix has to be, it has to be a 9 by 9 matrix. So it has to be a d² times d² matrix. And what I want to convince you is that if you look for a second at the identity matrix, just tensored with A, the way I want to convince you that this has this form here, well, it's actually quite simple to see. Right? If you have an identity, then here in this thing there, oh, I shouldn't have called this A and that A. That's very stupid. Sorry about that. So, but you see, so here, this is now an identity matrix. So A21 is, for example, 0, A12 is 0, and A11 is 1, and A22 is 1. So if I chronicle the identity with a matrix A, I'm going to get this diagonal matrix where on the diagonals there are all the A's sitting. Right? That's quite easy to see. And now I wrote it in a different way here. So here I write now my state vector here. I define these first three elements as y1, then the second three as y2, and the third three as y3. So this is actually a vector here with 9 elements, but I just written it in a shorthand notation with these 3 elements. And then I multiply this to this matrix here. Extremely simple. It's going to give me A times y1 times 2 times 3. But now you see these y are just going to be the columns. So this is just going to be your initial density matrix. Right? Because y1 is here, y2 is here, and y3 is there. Right? So in other words, if I do that, if I have the identity tensor product A, if I apply this to this linearized state vector, it's going to be equivalent of applying the matrix A from the left side to my density matrix. And in a very equal fashion, I'm not going to do it, I leave it as a simple exercise. You can also show if you have another matrix B and you build something like the transpose of this matrix, tensor product with the identity, you apply it to Y. This is equivalent of applying the matrix B from the right side to the density matrix. And in the same way, if I combine those two, that's then easy to see, is if I have something like, if I build a matrix which is the Kronecker product of a transpose of B and the matrix A, and I apply it to this linearized state vector, I'm going to apply A from the left side and B from the right side. Okay, this is some easy mathematical connections just using these tensor products. But you see, they allow you to kind of like, in an easy fashion, construct the full matrices, the full d squared times d squared matrix, in such a way that they either act from the left side on your density matrix or from the right side. And that's all I need for for writing down this the master equation. Right? Because in my master equation, I just have only terms acting from the left or some matrices going from the right. So here, I just show you exactly how this is done. I use the form, this is quite common, it's with the effective Hamiltonian. So here, this is the master equation written in terms of this effective Hamiltonian evolution and the recycling term. Now, let's look at this. So the effective Hamiltonian, of course, is super easy to construct. Right? I want to take the example where I now take this optical Bloch equation dynamics. So I take now for each of my spins, I take this Lindblad jump operator, which takes me from the excited state to the ground state with some rate, gamma. So the effective Hamiltonian is just simple. I just take my normal Hamiltonian, and then I just subtract from it all of it, this negative imaginary part with gamma over 2 times using again my lowering operators defined on the whole Hilbert space in the system. Very sparse. On the other hand, I have now sort of, wait, what am I going to do? Okay, exactly. So the only thing I really actually have to, no, exactly. So here now I have to write down this term. This is this coherent Hamiltonian type. And here I just write this again in my vectorized form. So here's the state vector that I introduced. And with using these rules, I apply here this effective Hamiltonian from the left side. So I write this as an identity Kronecker with this effective Hamiltonian that I constructed here. And minus H star effective from the other side. Why is this H star? Here is H dagger. But in my formula, I need the transpose of the matrix. So I just transpose the matrix. But then also I have in the original equation, I have like the dagger here, so I have to complex conjugate it. Right? So I just take the original effective Hamiltonian, I just complex conjugate every element, which is a bit flip, really just for every of these elements, super cheap. And then I Kronecker this with the identity on the right side. And by doing this, this is going to give me the part of the matrix A that corresponds to this type of term. The same for this last term here. For the last term, I can use this identity there. So I have this jump operator for my spin eta here acting from the left side and the daggered version acting from the right side. The matrix representation in the vectorized space is really just the L star again, element-wise conjugation, tensor with the actual jump operator. Good, so this is what I do here. Just 4 lines. The first line is really, I call, again, my full Liouville matrix, I call it A. The first line is just doing here this Kronecker with the sparse identity and the sparse Hamiltonian. Of course, everything has to be sparse, especially now that we are talking about d squared times d squared matrices. And then I just add these n terms that I get from this sum over there, again, using just my sparse version of the sigma operators. Here, a little detail, I just really only have to do a Kronecker between 2 of these lowering operators because they are actually real operators anyway, so I can forget about this complex conjugation step here. All right, very simple. So let's see what we get. Now, of course, sadly, right, everything I talk about here, it still has this problem of this exponential scaling in the system size. Now we made it more dramatic because our state vector is actually twice the size. So before I had 22 spins that I did on my Sandy laptop. Now it's only 11. So I show just this example here. This is again our transverse easing model. This is the short range case, so alpha 3. So I get the same type of physics before. I had sort of this initial nail state, spin up, spin down, spin up, spin down. And then my spin was going to before to this 0 value. But now actually, of course, you see it's going from white to red here. It's just because my atoms start to decay. Right? So here it's more scientifically, I just plot for 2 spins in the system, the number 5 and number 6. I start this one excited, it goes down, the oscillation is killed actually immediately, this one too, and then it slowly goes down because I'm starting to lose excitations in my system. Okay, but very simple additions. Now I can treat the whole system having also some dissipation. And I showed it here for this optical Bloch type spontaneous emission master equation. Of course, it was equally if you add some dephasing jump operators would be Lindblad operators with a sigma c term, for example, and it's a very general form of writing type of dissipations. Also, there's collective dissipation. If you have terms like superradiance, for example, if you treat full dipole interactions also with the dissipative part, you can all bring them into this Lindblad form and then solve it with this technique. Okay, one comment. This is one way of doing it. I use this analogy that I construct my Liouville matrix by understanding how to construct a matrix that I apply from the left or from the right to my density matrix. Actually, it's not the way that I would do it. The way that I would do it would take a little bit more work, but actually it's much more efficient to do a linearization of your density matrix using this kind of Pauli string operators. Right? Because in the end, if what I do is if I write down my snake for the density matrix, what I actually do is I define sort of 9 orthogonal matrices in the system for my 3x3 matrix, and then I expand my density matrix into these basis matrices. And if I do it in this snake form, I just use the orthogonal basis matrices, which are like 0, 1, and 0, 2, and 0, 3, and things like that. But they are much better basis matrices to use, and the Pauli matrices are a much better basis. So by Pauli matrices, I mean I define here my sigma matrices just with to the power 0, 1, 2, 3. To the power 0, I really mean to the power 0 because I mean the identity. And then sigma 1 and 2 and 3 is going to be sigma x, sigma y, and sigma z. Right? And as you know, they just form an orthogonal basis for any type of 2x2 matrix that I want to write down. Right? Simply because the trace inner product between matrix I, between n and m is going to be a Kronecker delta. Okay, and I can do this with a Kronecker product for all of my things, and this takes a little bit of work to construct now a vector. Right? I'm going to get this vector here, R, which is going to be a representation of my whole density matrix. It's kind of like the Bloch vector for the many-body case. Right? If I take one spin, then I have only sigma x, sigma y, sigma z. I have a 3-dimensional vector that describes everything. This is a generalization for many atoms. The main advantage here is that this vector that I get is going to be real, right? Just like your Bloch vector is real. Right? Because if you think about your 9x9 density matrix here, the off-diagonals have complex parts and real parts, and I can just write it down in a base in such a way that I only need to take care of the complex parts because row dagger is the same as row, so the down elements are just the conjugate of the upper elements. And then, of course, I can get away with more because then I do not need to store complex numbers in my memory, but I can store real numbers and can make things more efficient. But it's going to take a little bit of work to construct this, so I'm not going to go do that. Instead, in the last 20 minutes or so, I want to introduce a way that some of you know to overcome the fundamental problem here that we now have sort of limited ourselves to half the system size. So that's kind of sad, but we can do much better than this, just using this quantum trajectory idea. So that's the last thing I want to really discuss in more detail today. So the problem is that we really kept like the whole state of the system in form of this full density matrix. But sometimes this can be an overkill, right? Because maybe we don't even need to store all of the elements of the density matrix. And the starting point to understand how to exploit this is just by realizing, of course, that any density matrix, you can just write it sort of as really a statistical mixture of some pure states. Right, so the fundamental idea of this quantum trajectory technique, or also initially known as quantum Monte Carlo wave function algorithm, here introduced in the early 90s, is instead of sort of evolving this whole beast, which is the density matrix, is we just start usually from a simple pure state anyway. So let's just find some description of evolving the pure state instead, and just do this many different times, or like a few times, to get a good statistical approximation of our density matrix for the type of observable that we're actually interested in. Okay, so how does this work? So I just really describe how this algorithm works here in a few steps, and then I will show you why this actually evolves the master equation. So again, as always, we introduce a small time step in the system, delta t, and let's say we start in some initial state, psi 0, and let's now say we want to go to a state at times 0 plus delta t. And by state, I really mean I take one sample from this density matrix, one pure state, and I want to evolve that one state to further in time. So the way that one thing, at least that's how it's written in the books, in practice one does it a bit different, is that first I just do I pretend that my effective non-Hermitian Hamiltonian would be the real thing, and I just do an usual time evolution with this non-Hermitian Hamiltonian. So I take my state psi 0 and I just build the state at psi delta t. But then, of course, as I said before, because now it's non-Hermitian, so the norm of your state is going to decay. And you can easily compute numerically how much this norm decayed. So let's define a number, delta p, which is the loss of the norm of the state. So I get this new state, I just can compute the norm of it, and I do 1 minus this, and I call this number delta p. Okay, and now what I do is I just pick some uniformly distributed random number, let's say between 0 and 1. And then if this number is larger than this value of delta p, so this is going to be the likely case. Is it, or did I get it wrong? I think it should be smaller. Sorry, I think I messed it up. Okay, so this is in the most likely case, when you take a small time step, the norm goes down a bit, and if you put a random number which tells you that you're below that norm, then you just keep going on, and you just take your state at time delta t, you renormalize it, and you just go to the next time step. On the other hand, is kind of the rare events where you pick a number in such a way that it's actually fitting in this gap between 1 and the norm. Then what you can do is you have to just randomly apply one of these jump operators to your system. But we have many jump operators in our sum here, so we have to pick one. And then what one can do is one can compute this probability distribution, which is my state psi 0, and I take this L dagger L as an operator, and I compute this number, and I properly normalize it so that this is a good probability distribution. And then from this probability distribution, I pick one of my jump operators. Then I apply this jump operator to my initial state, and I renormalize the state and go back to the initial thing. Right, so this is really the way of evolving, that you kind of evolve over a little time step, and then you say, and this is something I will prove on the next slide, that the loss of the norm is kind of proportional to the probability of a quantum jump happening in the system. And this is algorithm, what it does, it just really does a simulation of this. It just asks in every time step, should I apply a quantum jump or not, with a small probability, and then it just keeps evolving it stochastically in this form. All right, so why is this working? Okay, so here is essentially very simple. On the next two slides, just to prove why this is working. It's quite easy to see. So let's say that we have a state at time t, and the starting state that I get is just like a randomly drawn sample from this state. If I'm at the initial state, I start in the nil state. It's anyway a pure state, and I just pick this state. Okay, then let's see if we apply this algorithm many times. Let's see what would be the average density matrix that we get out of this. Right, so the state then at times t plus delta t, if we start from a pure state, we have to describe it by like an averaged density matrix. And we had in this first case sort of this probability 1 minus delta p. So this is the most likely scenario. I just get like the state delta t that was over here. I just write it as cat psi delta t bra set psi delta t, and I just properly normalized it over there. So with this probability, I'm going to get that state. Right? Here I mean a statistical average because I did it many times. If I do it like 1,000 times, I'm going to get roughly really this first term of the Hamiltonian. On the other hand, in the second term with the probability delta p, which is the unlikely case, and with the probability p eta, I picked one of these jump operators, I applied it to the state psi 0, and I renormalized the whole thing. Right, so as a statistical average, at times t plus delta t, I'm going to get a density matrix that if I have an infinite number of samples, it's going to look like this. Okay, so why does this work? So there's one extremely simple math written down here. So let's just say we do a linear expansion of our state. So really just the first term in the Taylor expansion. So I keep only terms which are linear in delta t, and I neglect terms which are delta t squared. Then the state here that I get, psi delta t, would be from the effective Hamiltonian evolution would be psi 0 minus I effective Hamiltonian delta t applied to the initial state. Right, and this was just my definition of delta p. I write it over there. So what I want to do is, just for fun, let's compute what is in this linear approximation. What is going to be the norm psi delta t times psi delta t. Right, so I have to take this, I have to compute all of the cross terms, and I'm going to neglect the terms which is delta t squared. So I just get 1 minus I delta t psi 0 h effective psi 0, right? So this is when this term hits this term. And then I get the complex conjugate part of this when just this term hits that term in terms of written as a bra. Okay, and so this thing here, and I now write it as 1 minus 2 delta t times the sum over these things over there, right? Because this is just what this effective Hamiltonian gives me. Where have I written? I have it written over there, right? I have here the minus I part. So if I plug this in these equations here, I get actually a factor of 2 thanks to this different sign here and the minus I here. And I get in total a minus 2 times delta t of the sum of this term that I had before. Okay, but from this, what I can see now, if I compare now like this, what I computed the norm squared in this approximation. So I compare this norm squared with this definition of my delta p, and I can read off that my delta p is just 2 times delta t, the sum over all of these probabilities tilde here. Because this was just a definition of these probabilities before I actually normalized them. Right. So on the other hand, then just resolving this means that I can write my normalized probability for this value eta. I can write it as p eta tilde times twice the time step delta t divided by delta p. So this is just a very simple identity that it's going to true applying this algorithm if I assume just a linear order in this evolution. Okay, but this is actually this simple formula I just derived. It just immediately explains why this whole thing works. So what I just do is I just take this and I plug it into this sum here, and then let's see what we get. Okay, so here this is then psi plus delta t. So here is just again in this linear order. This is just going to be 1 minus delta p, right? Just by definition. This is what we used over here. So this is going to cancel that term. So the first part just really becomes psi delta t psi t. Right, so this is really the part that comes from the Hamiltonian part with the effective Hamiltonian. It's going to evolve me, and it's going to take me from a pure state to another pure state, if you like. But then you get all of these jump parts over there. And here I plug in this p eta over there. I see that I have a delta p here. It's going to cancel this one. And then nicely I have, again, sort of 2 times delta t. The delta, sorry, 2 times, oh, I'm confused. 2 times, yes, delta t, and delta t is going to stay here, but I have this p eta tilde, which I defined, which is going to be exactly the value that's going to cancel this thing down there. So in total, the effective equation I get, if I do a statistical average over this scheme many different times, I can write it in this form, and even with the right factor 2, you see that this is precisely really the evolution you would get from a Lindblad master equation. Okay. So what this means, if we apply this many times in each time step, we're going to get a very good approximation of the next density matrix if we do just a sufficiently amount of samples in our evolution. Okay, now important word of warning here. You see from this argument, this is really only true in the linear order, right? So before I told you all about this nice methods that you can go to very large time steps by using high order integration. But fundamentally, this quantum trajectory technique as written down, it has an error that goes as delta t squared. So one has to be careful if you want to have a situation where I have large dissipation rates. Because if I have large dissipation rates, it's important that I have to have my time step multiplied with this rate to be much smaller than 1. But so a situation where this is in particular very useful is where the dissipation is not so extremely large. Because then, of course, if I have sort of a gamma which is small compared to the coherent parts in my Hamiltonian, I can still use some high-order integration for my Hamiltonian piece to make that error from the Hamiltonian just small enough. But then I have delta t times gamma has to be small, and if gamma is small, this is going to be a good approximation usually. So it still makes sense to sometimes use some higher-order integration for this initial part of the simulation with the non-Hermitian Hamiltonian. All right, good. So in the same spirit as always, just showing you quickly how this is done. Again, all of the thing that I just was explaining here is just written in code over there. It has actually really almost exactly the same length. So this is one time step. Of course, we talk about random numbers now, so we need some good random numbers. On the computer, you have actually pseudo-random numbers. You have pseudo-random number generators, which are generated from some sequence. You give it some seed, and then from this seed, you get a series of quasi-random numbers. And it's important to change that seed if you run many trajectories. Otherwise, you run like 10,000 times the same simulation with exactly the same random numbers, and you wasted a lot of time. Okay, so we need this random number generator here in Julia. It's done with these very simple commands. And so here I do exactly that. The first step is really just doing the exponential with this effective Hamiltonian. Again, here I just use my Krylov space method because just I can and it's very efficient. Then I compute the norm of my state. And then if the norm is sort of larger than a random number, by default this takes a number between 0 and 1, then I just take my state as the one which I got from this evolution here, of course, renormalized. If not, I just do sort of this quantum jump, and then I have to compute my probability distribution. I do it down there, and then I renormalize, and then I keep going. Okay, and so what I showed you, and this is actually a very important point, what I showed you is that if you do this scheme, then approximately you get like at the next time step, you get an expression of your new density matrix in the system. So you have, say, a number of trajectories. So you have to run this nt times. And then you build sort of the statistical average, and this is going to approximate your density matrix. Now, of course, if you have a full density matrix and you're interested in all of the elements of your density matrix, then you're going to need a lot of trajectories here, right? And then you need actually a number of trajectories which is on the order of the size of your Hilbert space, and then you're not going to win anything, right? Then you're actually better off just simulating the density matrix directly. However, of course, in most cases, we just want to know how does some observable evolve as a function of time, right? And for simple observables, like the spins that I want to show you on the next slide, it's actually, you need usually much, much less trajectories than the Hilbert space size. And that's the situation where this kind of quantum trajectory scheme really is paying off. So how do I compute an observable? I get it just from this density matrix with usual trace operator rho. And then, of course, in this formulation, it's just I take just the expectation value with my trajectories of the observable, and I just compute the mean value of this. And that's going to be the evolution of the observable that I'm interested in. Good. So again, how is this working? I want to use the same example. So this is not trajectories. This is the exact calculation I did before for my 11 spins. Now, if I run these trajectories, of course, I do something like this. So this is really just for 10 trajectories in the system. I actually plot a few of them here, and you see they do some crazy stuff. Sometimes they're going down, then they go up again, and go down, and so on. But then if I take the average over those numbers that I get here, this is, again, my sigma c value on these sides I and 5, I see I get already to something comparing to the previous, which already starts looking like the real thing. But then, of course, it can get quite painful. Then I go to 100 trajectories, it gets much smoother. I go to 1,000 trajectories, it gets even better, but I still have a little bit of wiggles. And I was, of course, quite lazy here because, of course, you can draw statistical error bars here. That's what one should always do. I just didn't want to go through the work of doing it here. But you see, if you do this just large enough, you're going to reproduce exactly the same type of dynamics in the system. Again, so this is the main comment that I actually just mentioned before. This is really not useful if you really want to have some very complicated higher order correlation function in the system. Because the problem is the error that you have here, of course, it decreases statistically. So it goes as 1 over the square root of the number of trajectories that you actually use. And if you have some complicated correlation, which is typically very, very small, you have to get these error bars very, very small. Then you need a gigantic number of these trajectories. However, if you're interested in how the spin evolves or some 2-point spin correlations, this can be a very useful thing. Final comment also, why this is very nice, because it's in a way, these trajectories, right, you just need one computer for one trajectory. So if you have multiple cores or you have a supercomputer, you can just run all of these trajectories at the same time. So sort of, if you have like 1,000 nodes available on some supercomputer, then you can really produce this curve really only using the time that you would need for a state vector simulation, because these trajectories don't talk to each other. That's a next order correction. If you have trajectories that start talking to each other, you can get to some higher order thing, but then you cannot do this parallelization anymore. All right, good. So that's pretty much all the story I want to tell today. So just doing the recap. So I started off with just motivating everything today from this type of long-range spin model physics, which has already some complex things like correlation propagation with these quasi-particles, this short-range physics, which has a competition with this long-range buildup of correlations. And all of this, to do this, I showed you how to construct this type of spin operators, just starting really fundamentally from the spin lowering operator, which is really the only operator you need to write down on your full Hilbert space just for all of the spins in your system. And then from this, you can just construct everything, importantly using sparse matrices, because otherwise you waste a lot of precious resources. Then if you have a matrix and it's sparse, of course, you really do not want to build this full matrix exponential, because then you would go back to a full matrix. So you want to keep it sparse, so you want to have an algorithm that exploits the sparseness. This can actually be some Runge-Kutta method, because in Runge-Kutta you just apply a sparse matrix to a vector, so you never have to actually build a full matrix. But I think the most elegant method is the so-called Krylov space idea. So I motivated this. So really, this is a space that at each point in time you define from the state that you just have by just applying your evolution matrix to the state multiple times. And this is not an orthogonal matrix, so you have to use some type of iteration to some type of Gram-Schmidt procedure to turn this into an orthogonal good basis. So there are these two things, either the Arnoldi iteration or this Lanczos iteration. This is only working for Hermitian matrix. And generally, this Arnoldi iteration works for many different matrices. And then sort of what one does is you take your state vector, you project it onto this Krylov space, you do all of the complicated things there, like your matrix exponential, and then you project it back, and you're going to get a good approximation of the state that you have. And this is really super efficient. It really allows you to do 22 qubits or spins on your laptop. And then in the last part, I discussed this Lindblad master equation dynamics and how to simulate this. The most straightforward sim is this vectorization of a density matrix, so bring it into a linear form and write your Liouvillean, so all the right-hand side, your super operator, just write it as a matrix form. One can do this with this Kronecker product construction, or one can be a bit smarter and use this kind of many-body Bloch vectors, which are real, and then write evolution equation matrix for this thing. Alternatively, I can just, instead of evolving the full density matrix, I can just pick samples from the density matrix and have some stochastic procedure to evolve them. That's called quantum trajectories, and I introduced the most common way of doing quantum trajectories the last few slides. Okay, and that's it. So it just remains to count the people asleep, and then we can go to dinner. Questions?